puts out the fire. He says, why didn't you put out the fire? He says, last time I solved the problem. The problem was, there's a fire, there's a pitcher of water on the table. I solved that problem. I took the pitcher of water and took out the fire. Now I know how to do that. As a mathematician, all I have to do is reduce it to something I know how to do. So you change this complicated problem into what you know. What you know is pitcher of water is on the table. You're done. That's mathematical way of thinking. Mathematics is not about, multiplying two-digit numbers in your head. That's called A, arithmetic, and B is called wisdom. I can do a lot of that. That doesn't make me any better. It just means, A, I'm going to raise to do all of that. Because, as you may have guessed, Abraham Lincoln probably was a classmate of mine. Could have been. Yes.
So in a sense, it's using a lot of statistical probability and skill to determine the most optimal route to solve the problem.
Could be. I mean, not everything is statistics. It's about taking a given problem and making into little things you know how to do. Okay? For example, there's a famous proof by Euclid. This was about 2,300 years ago. That the square root of 2 is not a rational number, or it's irrational, which is a fancy way of saying it cannot be written as a ratio of two whole numbers. Right? It's a beautiful proof. I mean, it uses a proof technique that was not known at the time. It is called reductio ad absurdum, which is Latin for reduction into absurdity. I mean, think about it. Again, this is mathematical way of thinking. I need to prove that there is not a single ratio of whole numbers that is equal to square root of 2. Think about the immensity of the problem. There are infinitely many possible, by the way, countably infinite. You can actually count the ratios. There are also uncountable infinities, the real numbers. There are infinite possible combinations. I need to show for all of them that they are not equal to square root of 2. Even with computers, I can't do that. But here's mathematical way of thinking. I know in mathematics to follow the consequence of an assumption. So I'm going to assume that that theorem is not correct. So that means there exists a ratio of whole numbers that is equal to square root of 2. Okay? So I'm going to follow its consequences. Well, if there is such a ratio, if I square that ratio, that should equal to 2, right? And let's call it P over Q. That means P squared over Q squared is equal to 2. Or P squared is equal to 2 times Q squared. You immediately know that P squared is an even number. Well, only squares of even numbers can be even, so you know that P is an even number. We follow something similar, and so P is an even number. That means you can write it as 2 times K, K being an integer. So 2 times K squared is equal to 2 times Q squared, or Q squared equals 2 times K. That means Q squared is even, that means Q is even. So the only thing you know is that squares of even numbers are even, and if a square is even, it has to be square of an even number. So those are the things you know. Well, you just showed that both P and Q are even. That means I can reduce that fraction. Well, if I reduce that, I'm in the same hole. And there is a limit to how much you can reduce fractions. Okay? 2 over 4 can be reduced to 1 over 2, but that's it. At some point, you're going to hit a irreducible. Or you can immediately assume that that thing initially was irreducible. So whatever that ratio is, I reduce it to the simplest form. But that means I am able to reduce an irreducible fraction, which is an absurdity, okay? But that absurdity happened because I assumed the damn thing was not correct. If it's not correct, it leads to something absurd. That's why it must be correct. That's the mathematical way of thinking. I don't need to calculate anything, okay? It's following logic and little things. In fact, you can even, with slightly more complicated arguments, you can show that square root of any prime number is actually irrational. So you can put everything we know about the world in that number. Since irrational, that means its decimal form does not end. Oddly enough, you can represent square root of 2 in a computer exactly. Because computers with binary processors, they represent the numbers as 2 pieces. There's the base and there's an exponent, and the base is always 2. Well, square root of 2 is 2 to the power 0.5. In just decimal system, we can't represent it like that. Anyway, so if you open that file, first briefly talk about what we're going to use it for. We're going to talk about annuities. By any chance, anybody heard of annuities? It's okay if you haven't heard it. You probably know what it is, you just don't know that it's called an annuity, okay? An annuity is level cash flows, level periodic cash flows for a finite period of time. Can you think of an example that looks like that? Anybody here has a mortgage? Well, you may be too young for that. Anybody here has a car loan? Student loan? Okay. If you have a car loan, more than likely you don't have the cash to buy it. You go to a car dealer and you say, can I buy this car for $20,000 and please finance it for me? They say, okay, if it's a new car, we'll give you 7 years, you make payments of $400 a month. For the next 7 years, every month you're gonna pay $400. That is an annuity. Mortgage, for the next 30 years, they're gonna make a certain amount of payment. That's an annuity, right? We're gonna kind of expand it a little bit. Let's define some terms. We're gonna use R, this is the APR, for interest or discount rate. APR means annual percentage rate, because that's how interest rates are quoted. F is frequency of payments. For example, F equals 12 implies monthly. And period interest rate, which I'm not going to use directly, but APR over F, I'm sorry. So if your credit card company tells you that they're going to charge you 18% compounded monthly, they're basically charging you 1.5% every month. Okay? I'm going to call $C. This is the periodic payment. So your $400 a month car payment, that's your $C. I'm going to kind of extend this a little bit. I'm going to put a $B. This is a balloon payment. If we are dealing with present value of annuity. There's actually a very common example of this, which we're going to cover in chapter 6. But if you know anything about standard bonds, they pay a certain amount of coupon every 6 months. And at the very end, in addition to last coupon, they also pay $1,000. Okay, that's a balloon payment. In bonds, we call it a principal payment, but it's a balloon payment. But this is equal to a starting balance if we are dealing with future value of inventory. So if I told you that you got $10,000 now, and you'll be able to save $200 a month for the next 40 years, you can earn 8% a year APR. How much money you will have 40 years from now? That's a future value problem. So in those problems, $B is going to be the beginning balance. In present value problems, it's going to be the balloon payment. And I'm going to write a very dirty formula for these. Present value of an annuity with balloon payments is equal to, in fact, $C divided by R over F times 1 minus 1 over 1 plus R over F. Oh, I forgot to add one more input. T equals length of time in years. And that could be a non-integer number, 7.5 years, for example.